Welcome everybody to session 2 of Advanced Track for this quarter. We'll be studying string algorithms, and in particular, we'll be doing.
Raji's here.
Yes, everybody's here. Hello, Raji. Hello, Rishi. All right, so this week we're going to be looking at string algorithms, so KMP and Z in particular. No worries if you have no idea what that is. This workshop in particular has basically zero prereqs. There's like no sort of like advanced technique that we assume for this workshop. So let's get right to it. The problem we're going to be tackling pretty much this entire workshop is substring search. So you are given a text of length n and a string s of length m. And the question basically goes, can you find out if string s occurs in string t? And if so, how many times? Can anybody think of like a naive algorithm for doing this? I'm sure all of you know it. Just want to hear it from one of you. Feel free to unmute.
You can compare the substring to every substring in the main string.
Yep, that works. So we go and look at every substring of length m in our original string. And that's, order n such substrings, and you take order m time to compare each of them, and that's n times m. And that's too slow. We obviously want to do better. All the homies hate quadratic time. We want linear stuff. So this workshop, we'll try and find a way to do it in O of n plus n time. Now, for some of you who might already be familiar, you can do this in linear time with string hashing as well, but it is not deterministic and it's not as cool as the algorithms we're going to study today. So we will kind of ignore hashing for today. But if any of you do have questions about that, I'm happy to talk about it at the end of the workshop. Okay, so the first algorithm that we're going to be studying is called KMP. It's named after its three famous creators, Newt, Morris, and Pratt. And as promised, it solves substring search in O of n plus n time deterministically with a super low constant factor. Like, it's only the idea that's really big brain. If you actually look at the implementation of KMP, it's literally 4 lines. It's super short, barely any overhead, and like super easy to code. Okay, so before we get into how KMP actually works, I guess some preliminary information. There's something known as the prefix function, which will be useful. And we define the prefix function of the string to be the length of the longest proper prefix of s that is also a suffix. All right. So you look at the string, you look at it from the front, you look at it from the back, you try and find the longest prefix that is also a suffix. And note that we use this word proper here. All that means is the prefix cannot be the entire string. It has to be, a proper substring that is also a prefix. So let's look at a couple examples. The first string is A, B, C, D, E. Right? So the different prefixes that we have here are we have A, we have AB, ABC, and ABCA. Those are the 4 proper prefixes that we have. And it's quite easy to see that the longest one that matches is actually AB. And so that is our longest matching prefix. And if you wanted to assign a number to this, because the prefix function is technically the length of the longest prefix, you'd see. Okay. All right, moving on to the next one. ABABA. All right, does anybody want to take a shot at this one?
ABA, or just ABA?
Yeah, yep, exactly. That'd be ABA, right? And notice it's okay for like the prefix and suffix to overlap and all that stuff. We don't care about that, right? So that's ABA. Great. Look at a couple more just so that people are on the same page on what this prefix function means. So ABB, for instance, if you look at it, the prefixes are only A and AB, but there's no suffix that is A or AB. So in this case, the prefix function is just the empty string, or it has length 0. And I don't know, people can ask other weird questions if they want to annoy you, I guess. What is the prefix function of the empty string? I don't know. We don't care, I guess. It's technically not defined according to this prefix function because The empty string really doesn't have a proper prefix. So, whatever you feel like, not defined. All right. So now that we know how to compute this prefix function, we will define this thing called the P array, or the prefix function array, that computes the value of this prefix function for every prefix of your string. All right. So suppose this is the string that we have here, AB, AC, AB, AB. So then, okay, for convenience, by the way, we define P of 0 to be -1, but that's just useful for implementation. We don't really care about that. So for P of 1, for instance, we will look at the prefix function of this string. That's for this position. For this position, we will try and compute the prefix function of this substring. For this position, we will try and compute the prefix function of this substring, and so on. All right. So let's go ahead and do this together. Shouldn't be too hard. All right. So starting with A. Well, A doesn't have any proper prefix, so its prefix function value is just 0. Oh, you see, there's a different blue. All right, 0. Now for B as well, there's no prefix that matches any suffix of AB, right? That's also 0. Now when we look at this string, ABA, we see that the longest prefix that matches its suffix is actually the character A, right? So this is longest P function value of 1. Does this make sense to everybody so far? Feel free to Zoom react, type in chat. Anything works. Okay, cool. Likewise for C, it's 0. And then when you get to A, well, no prefix matches again, except for just the character A, so it's 1. And then for B, now it's 2. All right. Does anybody want to continue? What about for A, the next character A? No thoughts? People confused? Go back to the definition again. What is the prefix function of this entire string? We're trying to find the longest suffix that is also a prefix, or equivalently longest prefix that is also a suffix.
Is it 2?
Is it 2? Okay, so.
Is it 3?
Okay, I hear 2 different answers right now. All right, so I guess we can explicitly write out what 2 and 3 would mean. So 2 would correspond to a length of prefix length of 2. So that's AB, right? And the suffix of length 2 is BA. They're unfortunately not quite the same, right? So this prefix doesn't match the suffix of length 2. The prefix function value is not quite 2. I heard somebody else suggested 3, and that's actually right. So you have ABA, and on this end, you also have ABA, right? These two clearly match. And you can check that nothing longer works, because the moment you add C, things get messed up, right? So is it clear why the prefix function value at this position will be 3? So reacts. Are people confused? If you have questions about this, please ask right now, because the rest of the lecture is like very much based on y'all really understanding what this P array is even doing. Yes? Do people have an idea of what's going on? Cool. Okay. And I guess lastly for position 2, once again, just looking at the prefixes and suffixes, we see that the value of the prefix function has to be 2, because the longest one that matches is just AB and AB over here, right? You can check that nothing else matches. All right, so that is our prefix function. Great. But I guess the $1 million question is, why do we care? you came in here with the promise of learning how to do substring search, and instead you're computing some obscure array. Well, turns out, if you can compute the P array efficiently, substring search becomes really, really easy. All right. So suppose you're, back to our original question. You're given a text T and a string S. Now, what you can do is build this new special string R, which is S concatenated with some special character that doesn't appear in any of your strings, concatenated with T. All right. So that would look like this. So you'd put your search string here. You'd put some strange character in the middle, and then this is the text that you want to look for the string in, right? Now what you do is compute this P array for this new big string that you've created. And now I claim that checking whether the string S exists in string T becomes really, really easy. Because string S exists in T if and only if the value of the prefix function is M for some index I over here. Do people see why that's true? Consider some index here. Suppose that for this index I over here, the value of the prefix function is M. Well, what does that tell you? It says that the length of the suffix ending, the suffix of length M ending at this position I, which is this, is the same as the prefix of the entire string of length M, which is this. Prefix function being equal to M is telling you that the string that is over here is the same as the string that is over here. And that is exactly what it means for string S to be in T, right? Do people follow? All right, okay. Here's a small, quick challenge question for y'all, maybe. There's this, we put this pound sign or dollar sign or whatever, obscure character that doesn't appear in any of the strings. Why exactly do we, whoops, my screen get cut. Okay, why exactly do we need this sign? Like, would something go wrong if we just took S, T and put them together and just, computed this B function and did our usual stuff?
If we expect the substring at the start, it'll not catch it because we think it wouldn't be a proper substring.
If we expect the substring at the start, it would not catch it because it's a proper substring. Can you give me a quick example of where in the string it wouldn't catch it?
Like at the very beginning of at the very beginning of what T is.
Over here?
Yeah.
So if, for instance, maybe you look M characters over here, and then if you look at this position J, is the worry that your prefix function would not quite catch it?
Yeah, because if the pound side wasn't there, matching both M's would be like the entire substring up to that point, which isn't a proper substring.
Matching the entire...
Like if you have ABA and you want AB, the AB would be 0 because like ABAB is like the full string, I guess, if that makes sense.
Yes and no. Okay, so yeah, you do have a valid point that the entire string, by entire string I mean this whole thing is a prefix and a suffix that works, right? But by definition, our prefix function doesn't compute that, right? It just looks at proper prefixes and suffixes. So what is really stopping the our pre function from saying, okay, you know what? Here's a prefix that works. Remember, the string we're dealing with is like here through here, right? So I'm looking at this string, pretend the pound sign doesn't exist, by the way. And I say, okay, here's a prefix of length M, and here's a suffix of length M, and they both work. They're the same. So I don't quite see why the prefix function wouldn't catch it.
I mean, if it's like if it's AB,
Mhm.
you
Yeah, that's a good example. Let's look at that. AB. Yeah.
or like you're looking for AB
Mhm.
and like ABA. So then the beginning would be, so then your concatenated string would be ABA.
AB. Okay.
So then if you don't add the pound sign after the first AB,
Mhm.
when the prefix for like at index 3 be 0?
I do not. By index 3, do you mean this one?
Yeah.
I don't think so. In fact, we can go ahead and compute the prefix
Oh,
array
no,
for
yeah,
this
I
one
see it.
again. Do you see it?
Yeah,
I think that's a really good question, though. We should probably still walk through it because I'm sure other people have similar questions. So let's just compute the P array for this one here again, right? Doesn't hurt to do another example. So again, for position 0 is 0. For AB, it's again 0. ABA, we see that the first character matches, so it's 1. Now when we get to AB, we see that this is a suffix that matches this proper prefix, right? So the value of the prefix function will actually be 2. And then once again for A, it would be 3, right? Because ABA matches ABA. Does that make sense?
Yeah.
Okay. All right. That was a good attempt, though. Maybe here's kind of like a hint, right?
You put the pound sign there, or else the PI might exceed M when you want it equal to M, right? Yeah.
Right, exactly. Okay. That's a really nice observation. Okay, great. So as Gary points out, here's an example that we can consider. Let's say we're looking for ABC, ABC, and the text string is, oops, and the text string is ABCAB. Actually, this doesn't quite work. Maybe let's do ABC is our text string. All right. So now if you just concatenated them together and then ran your prefix function on this thing, you'd get, okay, like this, -1, and then 0, 0, 0, 1, 2, 3, right? But then what would the prefix function value be for this position?
4.
4? Yeah, exactly. Because the longest one that matches it is actually ABC8, right? So it'd be 4, 5, and 6, right? It just keeps increasing. And if you start looking for like, PI equals 3, you'll actually miss this occurrence of ABC. You'll only find this one and miss that. So yeah, I mean, it's a small fix, I guess, technically. You can do things like, okay, I will look for all prefix function values that are like greater than equal to M or something like that. You could have all kinds of hacky, fixes. But in general, just as a matter of like, I guess, hygiene, cleanliness, whatever, make sure you put the $sign or pound sign.
Even if you do greater than or equal to M, it wouldn't work for the example you gave, right? Because then it would account for 4 occurrences, even if it's just 2.
Right. Yep. Yeah. So okay, yeah, we can talk about it a little later, but you can technically use similar ideas like prefix function, like we do in KMP to like check the excess. But no, you're absolutely right. It's very ugly. We don't like that. We only want the pound sign, $sign, something in between. We don't want to deal with runovers. Okay, so at this point, y'all basically know how to do substring search real quick. Except for we didn't really talk about how to compute this P array quickly. So I guess that's the only missing piece, right? Let's go and do that. So the way we'll do this is we'll compute this iteratively. So we'll start from P of 0, P of 1. We'll just build our way up, P of 2, P of 3, P of 4. And every time we try to calculate P of I, we will try and use the values that we've already calculated. So when you're trying to calculate P of I, you try and look at like P0 through Pi minus 1, and somehow try and be clever about how you figure out P of I. Okay. So let's take this example string. here's our string S, right? And we are here at position I. Okay. Now, suppose we find a string, a prefix T, okay? That is also a suffix at this point, right? Can you say something about these prefixes and suffixes in terms of P I minus 1? In particular, suppose you have a prefix that matches a suffix at position I, right? So you have a prefix that matches a suffix at position I. Can you say anything about, so here's your position I minus 1, right? Maybe a little inwards here, okay? Anybody have thoughts? Okay. That's completely fine. Let's suppose this thing has length n, right? This matching prefix is length n. Now, what I claim is the prefix of length m minus 1 is a suffix at position I minus 1 that matches a prefix, right? So if you look at these m minus 1 characters, right? So just this part, and look at this part, they have to be the same, right? Can I get some Zoom reacts maybe? Yeah, see some thumbs up, yeah. All right, so this is the piece of, intuition, guiding intuition that lets us build this prefix function into effectively, right? So what is the idea that this gives us? Well, if we want a suffix that ends at I, so if we want a suffix that ends at I to match some prefix, then what we can do is we can look at the suffixes of I minus 1 that match some prefix, right? And then we can tack on this additional character if they match, right? Does that make sense? Give you all some time for that to sink in. So we look at a suffix of I minus 1 that matches some prefix, and then we try and see if we can just tack on this one additional character to form a longer prefix suffix pair. Okay, so that's basically your solution, right? So we have an idea now. We go through all suffixes of at position I minus 1 that match a prefix, right? And then we see if we can append the next character and form a longer suffix, right? But to be more precise, actually, we're only interested in the longest match, right? Our P function calculates the length of the longest prefix that matches a suffix, right? So what we can instead do is start from, we can iterate through the suffixes of I minus 1 that match a prefix in decreasing order of length and just pick the first one that works, all right? So here's another picture, right? So this is your entire string S, okay? So you look at the first suffix that matches a prefix, and then you essentially see, and suppose this is your character I, right? You want to calculate the prefix function at this position. You look at all the suffixes at position I minus 1. So this is your position I minus 1. You first check this position. You see if the character here matches the character here. If it does, you're good. You've found the longest possible prefix suffix match that you possibly could have. If it doesn't, oh well, let's try the next suffix that is also a matching prefix. All right. So we look at that one. Do these characters match? Well, if they work, you're done because this must be the biggest such one. If not, keep going, right? And at the end, if nothing matches, you just say the longest match is 0, right? Does this make sense so far to everybody? There's still one small point that I have not addressed, and that is, how do you find these prefixes that match suffixes, right? But apart from that, is the general idea or theme clear to everybody? I could get some quick Zoom reacts out of chat. And if you have questions, feel free to unmute at any point, as always. All right, so I guess the last part to the puzzle is, well, okay, the prefix function tells me what is the longest prefix that also matches a suffix. Cool. So at position I-1 over here, if I look at the value of P of S, it's going to tell me this position, right? So then I know the exact string that is the longest prefix that also matches the suffix at position I-1, right? And then I can just check the character at the next position, which would be at location P of S plus 1. I can compare it to the current character, and I'm done. Cool, right? But what if it doesn't match? Now, I somehow need a way to find the next largest suffix at I-1 that matches a prefix, right? The prefix function, remember, only gives us the longest one. But suppose the longest one doesn't work, and now we want to look at the next suffix that matches a prefix. Well, how do we do that? Here's where the KMP magic really comes in. The key observation is that these two, let's pick a nice color. All right. The key observation is that these two ret strings, so P of S tells you that these two are equal, right? Now you want to find the next biggest suffix that matches a prefix, right? So you want to find like some other suffix here that matches some prefix, right? But note that those purple strings are equal, right? So if you're looking for some suffix here, that is the same as looking for some suffix here. And now you're asking the question, what is the longest suffix in this purple string that matches some prefix of the purple string, right? And we know how to solve that problem already. Well, that is just the prefix function of the purple string, which we have already computed because it's a smaller value, right? So in particular, if the prefix, if this ret position is like P of S, then if you look at the prefix function of P of S, that will give you the next biggest thing that matches, and that's your blue thing here. So if you look at the prefix function of this dude, that will give you something here, which is the same as this, which is the same as this. And that is the next longest suffix that also matches your prefix that you're looking for. I'll give you all a few seconds for that to sink in. All right, it's a big picture, I guess, to summarize. You look at the string, all right? You look at P of S, by S, I guess here I mean I-1, right? You look at P of I-1. If you can extend that, great, you're done. If not, look at P of I-1, see if you can extend that. If you can, good, you're done. If not, look at P of I-1 and keep doing that until you find something. If you don't find anything, there is no match, and the longest matching prefix that's also a suffix is length 0. All right, time for questions. Did that make sense to people? Do people follow how we can go about doing this? Is iterating over all matching suffixes clear? Okay, I see some thumbs up on Zoom. All right. That's the case, we can move on to, I guess, code. As promised, coding this is super, super easy. So exactly what I said, actually. You, I guess, let me use this color. All right, you just initialize your stuff to all negative ones. You iterate through the string in order. You start with P of I minus 1, all right? This is what you start with. And then you try extending it. You check, so P of I minus 1 gives you something, and you are at some character here. This is where you are right now. P of I minus 1 gives you something. You check if this character is equal to this character, right? As long as it's not equal, you keep doing your P, you know, P of I, P of I, P of I, and so on, right? You keep iterating backwards. So that's this step, J equals P of J. So the first step, you're saying J equals P of I minus 1. If you continue this once more, it'll be J equals P of I minus 1, and so on, right? And finally, you just set PI equals whatever is, you know, the longest match you found plus 1, right? Because one character in addition matched. Well, what if no characters match, right? Note that this while loop terminates when it's when it falls less than 0. That's where our implementation trick comes in handy. If you set P of 0 equals -1, the while loop just exists when G is -1. J is -1, sorry, and then you set P of I equals -1 plus 1, which is just 0. Right? Make sense? Do people follow the logic? Cool. Yeah, that's exactly what we did. You know, in the last slides, right? I guess real quick, we can walk through the same, I guess, string that we've been looking at. So this one, right? We can look at the prefix function computation of this alongside the code, right? So that we have a good idea. So let's put this here. All right, so we start from I equals 1. Let me use maybe red. Okay, we start from I equals 1. J is equal to P of I minus 1. Okay, maybe I'll label these. 0, 1, 2, 3, 4, 7, 8. All right. So J is P of I minus 1. So J is just -1. All right, so this while loop never runs, and we set P of I equals J plus 1. So let me just write it. It's -1. This never runs. And then we set P of I equals -1 plus 1, which is 0. Okay. Let's go through this again. So now our J, maybe I'll keep track of J here. J is P of I minus 1, which is 0, right? Now we try to see if we can extend this match, right? So if S I minus 1, if A is equal to Sj, which is B, A is not equal to B, right? So we do J equals Pj again, and P of 0 is -1. J becomes -1. Once again, the longest match is 0. All right. Now, once again, J is set to 0 at the beginning of the loop. Now I guess I is 3, J is set to 0. Now we look at A, and is Si minus 1, which is S3. Oh, is there a typo here? Oh, I see. Okay. The string is the string is 0 indexed in this. If it helps, just for the sake of this example, pretend this is S sub I. Just for the sake of the example, it might be easier to understand. But anyway, S of I not equal to S of J. Well, J is currently 0, right? Maybe this is S of J minus 1. I don't know if it's easier for y'all. So just checking if A is equal to A. Well, A is equal to A, so this while loop never runs, and we set Pi equals J plus 1, which is 1. Once we get to C, again, we'll eventually hit -1 and set it to 0, right? Once we hit A, it's the same deal. just A matches, it's identical to what we did at position 1. So it'll be 1. Now, I guess it's interesting when we get to position 6. So position 6, you have I equals 6, J equals P of I minus 1, which is 1. Now, you are comparing, is Si equal to Sj minus 1? So you're checking if S6 is equal to the string at position 0, right? Here. And this does match, right? So now, this thing doesn't run, the while loop doesn't run, and we just increment j by 1. Or I guess we said pi equal to j plus 1. And we have pi is equal to 2. Do people see how this works? A little bit. We're slowly reaching a tricky case. So if people are confused, let me know right now. Are we good to keep going? Okay, I will keep going then. All right, so now, now I guess we're looking at I equals 7. We said j equal to p of I minus 1, which is 2, right? Now we check, is Si equal to Sj plus 1? So our Si is this A, and Sj plus 1 is this A again. And we ask, are these equal? They're equal again. So this while loop once again doesn't run. We exit the while loop, and we set Pi equals j plus 1, which is 2 plus 1, which is 3, right? And for the last index, which is finally the interesting case, here we have I equals 8. J is P of I minus 1, which is 3. Okay. Let me clear up some of this mess. Okay. Now in our while loop, we're asking, is Si equal to S of j plus 1? Right? So Si is 8. S of j plus 1 is 4. Right? We're asking, are these two equal? Right? Again, taking a step back, maybe, why are we asking, are these two equal? Because we already know from our calculation of prefix function that this ABA and this ABA are equal. So we're trying to see if we can tack on another character, right? Just taking a step back for a sec. But yeah, we're asking if these two characters are equal. And this time turns out they aren't. So our while loop is finally running for once. And we said j equals p of j, right? So j equals p of 3, right? So j now becomes p of 3, which is equal to 1. Okay. Look at what just happened now, right? So now we go ahead and check, is Si equal to S of j plus 1? So now we're checking, is this character, j plus 1 is 2 now, is this equal to this, right? And I guess once again, just take a step back to try and understand what we have effectively done. We have now found the next longest matching suffix until position 7, right? That is also a prefix. And now we are seeing if we can tack on another character to it, right? And this time, they are indeed equal, right? So we exit our while loop, and we set P of I equals j plus 1, so j is 1, and we set P of I equals 2. And this is exactly what we started with. Does that make sense? Do people follow? Quick Zoom reacts, maybe? All right. That's looking good. Okay, y'all are claiming that you understand it. I will make you implement it in like 10 minutes or so. So you better really understand it. But before that, quick tangent, I guess. Well, not tangent, very much important and related, but time complexity. So I claim that this is linear, right? We said the whole point of doing this whole prefix function thing is, okay, I told you we can do substring search in n plus m. And then I also told you how we'll try and figure out, the substring search if we have the prefix function efficiently. So it's clear that, if I'm not making a fool of everyone here, the prefix function calculation must be linear, right? But it's not entirely obvious why or how, right? So we're iterating through the string, right? So this for loop is linear. Like all these things we're doing inside are all single operations. That's all good. We don't care about that. The only sus part is this while loop, right? It's like we're at the string, we look at some position, and we almost like jump back a few times. And it's unclear how much we're really jumping overall, right? It's not immediately clear why this is linear, right? It just so turns out that, with KMP, it's easiest to understand time complexity by looking at the code. The key observation here is analyzing this value of J, all right? Note that J is somewhat like a counter that keeps track of longest matching prefix so far, kinda, all right? We set J to something, right? So J is initially set to something. Then in this loop, the value of J only goes down, right? When we do J equals P of J, recall that the prefix function by definition only stores values of proper prefixes, right? So P of J can never be equal to J. Like P of J has to be something less than J for sure, right? So in this while loop, the value of J always goes down, right? And at the very end, we do J++, right? We increment the value of J by 1, okay? It's effectively incrementing the value of J by 1 because once we are done with the loop, we go back and we set J to like the previous value of the prefix function. And this thing is the same as this, right? From the previous iteration. So overall, if you look at what happens to this value J, well, J initially starts off as P of 0, which is -1. So initially J is -1, right? In this loop, inside this loop, J can only go down, right? And every time outside the loop, we increment J by 1, right? Since this outer loop only runs n times, J can only be incremented n times, right? At most n times overall, right? Which means this while loop can only go down n times. Note that we don't let these values run below 0, right? You can only decrement J as much as you increment it, right? We only increment J at most n times. And in this while loop, the value of J only ever goes down. But if you incremented it only n times, overall, J can only go down at most n times, right? So this inner while loop, if you look at it overall, amortized, it runs at most n times. This is order n, and we already know the rest of the stuff is order n. So overall, the time complexity is linear.
Yeah, thanks. I thought it was a good explanation, and makes me wonder why I thought this was so hard before.
Glad you understood. Yeah, the KMP is always tricky. I remember it was weird for me when I learned it first too. I think part of the reason is just that the code is like very mysterious. Sorry, give me a second. Yeah, the code is a little mysterious in that the code being so short actually becomes a bad thing when you try and figure out what's going on under the hood. Like this while loop is like very suspicious, right? As I mentioned, it's very unclear why it is kind of but yeah, glad to know that this helped. Hopefully everybody's clear on how this works. All right. So now it's implementation time. There's this very neat problem on Cantor's string matching that I've linked in the slides. And it is the exact problem that we've been talking about. Given a text T and a string S, find all the occurrences of S in your text T. That's pretty much the entire problem. I'll let you all go and implement KMP to solve this problem on Caddis. And I'll give you like about 10 minutes or so to do this, and we can resume that. I'll pause the recording for now. Okay, welcome back, y'all. Hopefully you got to see some nice green ACs. With that, we can move on to the next algorithm on the agenda today, and that's Z algorithm. Same story, actually. Solves the same problem, substring search in O of n plus 1 time, deterministically, no randomness, super similar to KMP, actually, but it's a slightly different idea. And depending on the problem, sometimes it might be easier to work with the Z algorithm as opposed to KMP and vice versa. But for the most part, they're kind of equivalent. So at a very big picture, so if you look at a string, any string S, right? What exactly do we do in KMP? For any given position I, we ask, what is the longest thing to the left of this position I, right? That matches some prefix, right? This is the question we asked in KMP. Now, if you go to Z, you ask pretty much the exact question, but kind of flipped. So if you're at a position I, you ask, what is the longest thing starting at I, but to the right of I, that matches the prefix of the string? All right. So hopefully you all can already probably appreciate like how similar these are. They're kind of just like flipped in some ways. But interestingly, the algorithm itself is, I want to say, significantly different to the one from KMP. But the idea is we will compute a similar quantity. So for KMP, we looked at suffix ending at that point. For Z, we look at substring starting at that point to the right, that matches some prefix, and we'll do similar stuff. Okay. So same story again. We define something called the Z array, right? Z of 0 is 0, just for convenience. I don't think we'll ever use it. And Z of I is the length of the longest substring starting at I, that is also a prefix. Okay. By now, you all should be super familiar with how this Z function is computed. So it's pretty similar to the P one. So we can go through this a little quicker, right? So if you look at position A, well, A matches A, and that's the best thing, you can match. You start looking from A to the right. What's the longest thing that matches? It's just A, right? Because if you do anything longer, if you look at AB, that does not match a prefix. All right. The value of Z function at this position is 1. When you come to this position, well, any string from this point on to the right starts with a B, but our original string does not start with the B, so there's no way there's any prefix that matches. So the value of the Z function is 0. Okay. Now we are at this position. We're here. If you look to the right, the longest string starting from here that matches a prefix is AA, right? Because if you try and extend it any further, you get a B, and there's no B over here to the right. So the longest string starting from this position to the right is AA. So the value of your Z function is 2. Okay. Does anybody want to take a shot at the value of Z at this position?
4.
Yep, exactly. Longest thing that matches is AABA. And then you can see at the next positions they differ. This is an A and this is a B. So this is the longest thing that matches. So it's a 4. Likewise, we can fill out the rest of the array. For this position, it's 1. B, the first character doesn't match, so it has to be 0. Once again, for A, it's 1 because the first characters match. And for B, again, nothing matches. So it's 0. All right. Same question as last time. Why do we care about the Z array? Exact same story. Suppose we're given 2 strings, a string S and a text T. What we can do is compute the Z array on this new special string, which is R, S concatenated with some special character, concatenated with T. And then you calculate the Z array for string R, and the same story applies here too. If you find any position here where Zi is equal to M, where M is the length of this string S, so the thing to the left, then you know that you have found this string in your text T, right? Going back, I guess, one step, what does it mean that Zi is equal to M? it means that if you look m characters this way, the m characters that you see here are the same as the first m characters of the string, right? Prefix of length m. So this is telling you that the characters over here are the same as the characters over here. The characters over here are precisely m. So if you ever find a location where zi is equal to m, then it means that you have found the string, and vice versa. It's if and only if. Hopefully that's clear to everybody, right? The same idea as what we had for KMP with our prefix function. All right. How do we want to compute this? First idea that comes to mind, right? You look at each position in your string. Yeah, given a string. Some string. You want to calculate value of z for position I. You kind of keep like, you know, 2 pointers, one at the beginning of the string, one at your position I, and you kind of move both of them to the right as long as they match, right? So suppose this is your string. Suppose you want to find z at this position. You look at this character and this character. If they match, great. Move on to the next one. Do these match? Okay, wonderful. Move on to the other one. Oh, do they not match? Okay, we have ended, and our z functions value for z function is 2, right? Does everybody follow this? Yeah, just the simplest way you can think of computing z. But what is the time complexity of this method? Is this the beloved O of n that we care about? Or can it be worse than O of n?
N squared?
N squared? Yep, that's right. Can you think of an example? Maybe like an example of a string.
What about like AB, 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 AB repeating?
Yep, that works. Jacob's example was AB, 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 AB. Keep doing that a bunch of times. The point is, when you look at this A, you will have to go through all the characters to the right. When you look at the next A, you once again have to go through all the characters to the right. And overall, this is the order n squared, right? Maybe a slightly simpler example might be just a string of all A's, right? Now you started this location, and then you got to go through all n minus 1 locations. You started this one, you got to go through all n minus 2 locations, and so on, right? This is clearly order n squared. Once again.
Oh, okay. Yeah, maybe I didn't look closely at the algorithm. I thought you were like trying to build off of what you had previously somehow. Like the AB example, like thrashes between like 0 and something over and over again. But yeah.
Yep. Yeah. So every time in this naive way, I guess we start from k equals 0, and we assume we haven't matched anything. Yeah. Clearly, this is no good. We want to do better. So the question we can ask ourselves is, well, what can we do better, right? And the kind of idea or insight is maybe we should be making more use of the information that we already know, right? So we're computing these z values in order, right? We have everything till zi. Zi minus 1. Can we somehow make use of the things we've already seen so far to be a little more clever about how we figure out zi? Yeah. Here's the big brain trick, right? We maintain this interval LR, this thing here, that corresponds to the rightmost substring that is also a prefix of the given string, right? So let me repeat that once more. Our interval LR corresponds to the rightmost substring that we've seen so far that is also a prefix of the given string. So suppose at some point that we found that this section is the same as this section, right? So our LR would be this. Okay. Now, suppose we want to try and calculate the z value at position I, right? I tell you that we're maintaining this value LR, given that you now have this, can you be a little more clever about how you figure out CI? Like the naive way you do this is you start from here, you look at this position, oh, does it match? Okay, cool, so this matches. How about this position? Does this match? Okay, this also matches. And you start building from here, right? But can you maybe improve on it like a tiny bit more? You already have this information that this LR chunk is the same as this. Can you maybe do anything about it? I'll give you all a few seconds to think about it. It's completely fine if you don't figure it out. It's a little non-trivial, but hopefully just thinking about the problem for a little bit will be helpful.
So Nikhil, when you say the rightmost substring that is also a prefix of the given string, is this, are we just looking at the string up until the point that we've processed, or is this for the entire string? Like there's only one for one input? It's
a great question. It's for as far as we've processed. So it's as far as we know so far, what is the longest one? So when I say we're maintaining this LR interval, what this basically means at some index like J over here, right? Pretend we did our naive like computation or somehow, and we expanded our window all the way till here, figured out that Z of J corresponded to this string, which is the same as this, right? And now this is like the rightmost string that we also know to be a prefix.
So it's like the maximum value of J plus Z of J that we've computed so far.
Exactly, precisely. Yep. We keep track of yeah, so J plus Z of J, whatever the max value is, we keep track of that. So like argmax of that and the value itself. All right. So I guess here's a small hint, okay? Can we identify an other character in the string, in this prefix, that is the same as the character at position I? Yes, right? If you, like, given that these two yellow strings are the same, this character I exists here as well, right? So let's call this, well, we don't need to give it names because we know it's exactly the character at position I minus L, right? Does everybody see that? This is position L, this is position I, right? So the length of this is the same as the length of this. So this is character I minus L, right? Okay. Now, we are asking the question, we want to try and expand the string to the right. Maybe let me use a pen for this. We're trying to expand the string to the right and find like a prefix that matches it. Do we already know some information about this? The answer is yes, right? In particular, if you look at the value of Z of I minus L, Z of I minus L tells you the longest string to the right, starting from Z of I minus L, that is the same as the prefix of the string, right? In particular, for a more concrete example, suppose Z of I minus L ended exactly at this point, right? At the end of your yellow region. Then what can you infer from this? You know that this is the same as some prefix here, which is also the same as this string here, right? Remember that the yellow regions are the same, and this I maps to I minus L here. Excuse me. So everything that comes to the right of I minus L within the yellow region is the exact same as everything that comes to the right of I within the yellow region, right? So now when you're doing your while loop, extension, when you're doing, okay, as long as the characters match, do K++, you can effectively skip over this part because you already know they match, right? that make sense to everybody? People follow? Okay. So that's kind of like the main idea. Like, this is how we want to reuse information that we already know. So we look at z of I minus L, and that tells us something about, how much we might be potentially able to skip. So if you've started thinking about this already, you'll realize that we kind of have like, 3 cases to consider here, right? Depending on how big z of I minus L is compared to the yellow region, right? So we have like 3 cases. So let's look at them. Let's look at like each of them separately. So I'll make some copies of this. Okay. So the first case is z of I minus L covers everything exactly up to this yellow region, right? We've looked at this already. And that matches some prefix, and we know that is the same as this part. So when we are doing our while loop starting from I and moving to the right, we can effectively skip the red region and start our while loop from here, right? We can start comparing characters from here. So we've done a little bit of an optimization. Is this case clear? Okay, cool. Now, what if z of I minus L is actually bigger than the yellow window? Okay, so here's our yellow window. And suppose z of I minus L is some big thing that extends past the yellow window. That matches some prefix, cool. And the red part is, oh, well, I guess that's a question for you now. What can we say about the things to the right of I?
Again, we're going to have to check these like previously unchecked values.
Right, exactly. So all you can infer is that the only thing you know is that this yellow part is the same as this yellow part. Beyond the yellow part, you don't really know anything. If you look at this character over here, you do not know if it's the same as this. So you cannot really reuse the value of z I minus L like that much also. You can only use it to as far as you know. So you know that this yellow chunk is the same as this yellow chunk. So the only part you can safely skip is the part till here. So until you hit the end of the yellow region, you can safely skip until there. But once you pass the yellow region, you need to like sort of like brute force check again, right? You can think of this end of the yellow region as sort of like our boundary of knowledge, right? It's kind of like what we know so far. And anything within that, we're safe, happy, comfortable to do. But the moment you venture outside this R, which is like your boundary of knowledge, you need to start checking things manually. You're unsure now, all right? Now, the last case to check if z I minus L actually falls within the end of the yellow region. Same deal, matches some prefix, matches this, but it ends before the yellow region. What can we now conclude?
That it can't possibly be longer.
Exactly. It cannot possibly be longer because these yellow regions are the same, right? In particular, that means the characters over here, I guess these are very small, but okay, the very next character to the right, so this one and this one are also the same. But because z I minus L gives you the length of the longest string starting here that matches some prefix, you know that the next character, like in the prefix, is actually different. It's a purple thing. It's not our green, right? So these two are not the same, right? Which means this and this are also not the same because these two green dots are the same, right? So you cannot possibly do any better. You've already figured out what the longest string starting at this point that matches a prefix is. So in this case, you're done early, actually. You can just set zi equals zi minus L and call it quits. You're done. Are the 3 cases kind of clear? To summarize, if the part you're extending of the solution you found falls within like your boundary of knowledge R, right? Then you're done. You can stop. But if it's at R or if it extends beyond R, then you can safely skip everything up to R But starting from R, you need to, once again, like do your character by character checking. Is everybody clear on this? Can I get a few Zoom reacts maybe to see where people are at? All right. See a few thumbs up, so I'm going to move on. All right, so we can just translate this to code. Just once again, super short. I guess people could argue it's slightly longer than KMP, but come on, I think it's pretty good for a linear substring search algorithm. So this basically does exactly what we've been talking about, all right? So we initialize L and R to -1. Let me switch to yellow, sorry. We initialize L and R to -1. Now, K is a variable that tells us how much to the right we are free to skip, okay? Now, based on the example we saw here, how much are we free to skip? We have two cases, right? If the boundary is less than R, so if like I plus ZI minus L is less than R, then we're done, right? We don't have to skip anything, or like, yeah, we skip some part, we're done. But otherwise, if ZI minus L is bigger, so I guess it's the same as ZI minus L is less than R minus I, right? Otherwise, if it's at least R, so this is case 1, right? If I plus ZI minus L is at least is greater than equal to R, right? This is the same as saying ZI minus L is greater than equal to R minus I, right? In this case, we want to start doing the case check, right? Okay, so that's precisely what we do. This is just quick and dirty code to do that. So you do min of R minus I and ZI minus L, right? That effectively tells you the point to which you can skip through. And then after that, you start doing your character by character comparison. So you look at I plus K and you look at K and you check if they're equal. And as long as they're equal, you keep incrementing K. This is the same while loop we had in like our naive implementation. And then once you're done implementing K is now has like, the longest possible length, and you set ZI equal to K, right? And the last thing you need to do is update, your boundary of knowledge, right? So if it so happens, okay, so where are we right now? We're at I, right? I'm sorry. And we found that ZI to the right matches a prefix. So the new R value, as Jacob pointed out a little bit earlier, is I plus ZI, right? If this value is bigger than the R value that we already have, then we want to update our new L and R. So again, our L is just I and our R is just I plus ZI, right? That's the update we do. And we continue, right? So if you compare it to our naive version, we've not done much different. All we do is maintain this, window of knowledge, so to speak, right? We introduce this variable K, which lets us effectively skip some amount based on how much we know, right? Based on the old stuff, we skip a certain amount. Then for the rest, we do our old while loop check and we just update our boundary delimiter, right? Nothing different, nothing too different. But it turns out this optimization that we just did, although it was simple, is actually good enough to give us the linear complexity. So the time complexity of this algorithm is also linear. Same deal with KMP, actually. It is initially a little unclear maybe why this is linear. Maybe it's slightly more easier to see than KMP, but it's still a little non-obvious because of this while loop that we have in the middle, right? So zooming out big picture, we have this for loop that iterates through the entire string. And these are all like O(1) operations, right? All this window update, setting K, blah, 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 everything's O(1). The only part we are really concerned about is this while loop, right? That's the suspicious part. It might be initially unclear how long this while loop is running because we have I plus k less than n, and that seems like quite a lot, right? But the thing to notice here is that our window of knowledge only gets incremented. Like the maximum value of our window of knowledge is like n minus 1, right? So we have our string here. We're maintaining some window of knowledge, right? I guess a different, maybe slightly easier question to ask is, when do we do these comparisons, right? When do we do these comparisons and manually increment k? We do this only when we have exhausted our window of knowledge and we're trying to extend it, right? So if this is your LR bound, you enter the while loop only if you ever end up skipping all the way through here and you still need to check more characters, right? Now, the point is, if you ever end up extending past though, like suppose you go past your while loop actually runs, then inevitably, wherever you go past, right? Suppose you run the while loop a few times. So this part was your while loop. The point is, once you've extended it, you also update your boundary of knowledge, right? So now your boundary of knowledge has now moved. Maybe I'll leave that there, I'll use a different color. Your boundary of knowledge has like moved here. This is your new one, right? So the key thing to observe here is that every time this while loop runs, your R must be incremented. Every time you do this plus plus k, in reality, you're actually doing a plus plus R, because in the end you set R equal to I plus Zi, and Zi is just k, right? So the while loop runs if and only if you increment your boundary of knowledge. But how far can this R really go? It can only go to the end of the string, right? So it can only be incremented like n minus 1 times or n times or whatever. So this inner while loop runs overall at most like order n times. And so the overall complexity is once again linear. Does that make sense to everybody? This is also one of those weird instances where it's often, it might be easier to understand time complexity by looking at the code, and then it becomes a little more clear as to why this is linear. All right, do people have questions? All right. See something in the chat? Okay. All right. We can move on then. So once again, this time I encourage you all to solve the same string matching problem, but using the Z algorithm. Hopefully you all should be comfortable with it by now. Just for the sake of time though, I will skip through this, and I just have a couple more slides that we can quickly run through, and we have some practice problems at the end. So while you all work on the practice problems, you can also implement this using Z algorithm, and we can do all the problems at the end. So just for now, I'll skip it in the interest of time. But I guess I just wanted to end this lecture with a note about just the general usefulness of KMP and Z algorithms. It might seem as though, at least just based on today's lecture, that okay, you're computing these obscure like P and Z arrays in some clever way, and then you're doing substring search. Cool. This is the end of story. Well, actually, no. The prefix function and Z function can actually be used in like a wide range of scenarios. You will definitely see a bunch of this in practice problems. Sometimes it might just so happen that the Z algorithm, you don't even use it on strings, like you use it on an array of integers. Like it has all kinds of use cases. Hopefully, once again, you get like some taste of this with the practice problems. But here's just like, one example that I have for you. So suppose you're given a string S and you want to find the longest prefix of this string that is also a palindrome. How do you think you might do this? Of course, I mean, the naive solution is just you look at every prefix and check if it's a palindrome, right? But checking if a string is a palindrome is O of n, and there are n different prefixes to check. So this would be eventually O of n squared, which is not good. But I claim that you can use the KMP or Z algorithms, whatever you prefer, to solve this problem in linear time, in O of n time. I'll give you all a couple of minutes to think about this and let me know if you have any ideas.
Could you maybe reverse the string and then join it with the original one with like a separator?
Yep.
And then you want to look for KMP of the last, like the very last value in the prefix array or something.
Exactly. Yeah, great idea. So suppose this is your string S. Jacob's idea is you concatenate it with the reverse of the string, all right? You compute the prefix function on this big string now. And now the point is, if you look at the value of the prefix function at the last position, that should tell you the longest prefix that is a palindrome, all right? Suppose the value at this, the value of the prefix function at this point is like 5 or whatever, right? So what does it tell you? It tells you that the 5 characters that end here are the same as the 5 characters that end here, right? Now, if these are the same, note that this string is reversed, right? So your actual string actually starts from here and goes this way, but you've reversed the strings, and this is precisely what it means for it to be a palindrome, right? So this is like, if you want to index them, this is like 0, 1, 2, 3, 4. And because this string is reversed, this is 0, 1, 2, 3, 4. And if a suffix matches a prefix, then that is exactly what it means for it to be a palindrome, just by construction. Because you've reversed the string, 4, 3, 2, 1, 0 being the same as 0, 1, 2, 3, 4 means it's a palindrome. And in particular, the prefix function gives you the longest matching prefix. And that is exactly what we want. So now we have the longest prefix of a string that is a palindrome. Does that make sense?
You can also do this. You can do the same construction for Z algorithm, right? But you won't be looking at the last one. You'll be kind of iterating through the second half and then looking for like one where the size of it matches just so it reaches the end of the string.
Exactly. So yeah, this is a general theme actually. In fact, if y'all have time and you want to try out some fun problems, you can also try generating the Z array if you're given the prefix function array and vice versa. They're actually very interchangeable. That should seem pretty intuitive based on the figure we saw at the beginning of like Z algorithm, right? It's like one is computing a very similar quantity like leftwards and the other one's computing it right. So it does make sense like intuitively that these are very close to being the same. And so it's reasonable to expect that most problems that can be solved with KMP also have a Z algorithm solution. And it turns out that's often true. So as Robert points out here, like this exact same problem, you could solve it with the Z algorithm as well, right? Now, suppose you use the Z algorithm here, and you look at, Z of like some position. Well, it will tell you the longest string starting at that point that matches a prefix, right? But you are interested only in the prefix of the string, the original string, that's a palindrome, right? So remember that prefix of your original string is a suffix of your reverse string, right? So you're only interested in strings that end exactly at the end, right? So if at any position you find an I, right? If you find an I such that Z of I goes all the way to the end, so in particular, I plus Z of I is equal to N, then you know that you have a prefix that also matches a suffix. And now this gives you a palindromic prefix, right? The
It might
only
be easier to detect this inside the implementation of the Z algorithm because this is just when the value R reaches the end of the string, right? So
correct.
I already have an if check for that. So
Yep. That is a very good point. So Jacob's point was that you only care about palindromes. So palindromes is a prefix, right? So as soon as you hit the end, you are done. So at any point, you set your R to n-1 or n whatever based on your indexing, you're done, right? And yeah, I guess if you do pre-compute the Z array though, just make sure you iterate from left to right and pick the first one because you're interested in the longest palindromic prefix.
So I had a kind of maybe more abstract question. So I've noticed that, okay, so clearly if a problem is solvable, like if some function of a string is determined by the prefix array or KMP, sorry, like the KMP or the Z array of a string, like how the Z array is determined by the KMP array. Okay. Then clearly it must be invariant under permuting the letters that make up the string. Like it can't be a property like, well, okay, even this is like, if you do the extended like construction, maybe you could, but just like processing a raw string, like it can't be like, oh, how many A's are there, because KMP doesn't really know what an A is.
Right.
So I've noticed that typically when the problem is independent of the letters, like of permuting the letters, then it tends to be solvable using just the data in the KMP array. Is there some, do you know if there's like a result, like is there a characterization of which problems are use only the data in the KMP array, slash like, could you say something like, oh, if this problem is invariant under certain transformations, then the KMP array is enough to solve it?
Oh, that's very interesting. Short answer to your question is I'm unsure. In general, I feel like a lot of the problems, a lot of string problems in general, seem to satisfy like the condition that you mentioned to some extent. Like for instance, it could be like finding like a subsequence of some form, maybe, right? Even then, like if you just you found a permutation of the letters and like just changed everything in the input. Once again, like those kind of problems are also like invariant to like the particular characters, right?
And they're not solvable by K, or the KMP array is not enough to tell you. Like, I like, okay, find the longest like subsequence of distinct letters or something, clearly invariant under permutation, but totally unclear if KMP can say anything.
Yep. Yeah. But like that's just a little bit of intuition I have. Like maybe there is more to it. Like people have probably studied this a little more, and there are maybe certain classes or flavors of problems that are very obviously like, you know, KMP vibes. I'm actually unsure about that. Maybe I can, you know, read up on it a little more after and get back to you. But that's a very interesting question though, because it definitely is very interesting also from just a problem solving point of view, right? When you look at a problem, like how do you know if like KMP or Z is even something you want to think about? Because most problems, any new problem that you see, especially like in contest, odds are they're not going to be asking you, hey, here's a substring, find it in the text. It's definitely something that's much more sophisticated, something that'd be like, you know, it'd be KMP hidden. Like we saw in, I guess, the week 1 workshop where like there was Dijkstra out of nowhere. Like this would probably be like a similar story. So very interesting question for sure. We'll think about it and get back to you.
Yeah, I guess I feel like it feels a little bit like the spectrum or like the set of eigenvalues of a matrix, where it kind of like boils down the matrix into what's usually like the most important data, but then with the matrix there's a clear characterization of like the eigenvalues are like the interior part of the Jordan normal form, or like is the part of the matrix that is invariant under like similarity transformations or like change of basis. So that's why I was asking, like, oh, is the KMP array like the part of the string that's invariant under some transformation. I guess clearly simply permuting the alphabet is not enough. Maybe there's some family of transformations.
Right. Yep. I think it's an interesting just thing to study, right? Like, what sort of transformations is this invariant under? Very nice insight, though. It never occurred to me to think of the KMP array as some kind of, minimal identifier, like, or like some kind of canonical identifier of like, a string. It's definitely very interesting. Cool. Okay, we can chat more about it a little after. I see we're hitting the end of time. So I'll quickly move on to the last couple slides. It'd be great if all of you who attended could take a couple minutes to fill out our feedback form. I will give you time right now for that. But otherwise, if you go to the presentation, we have linked a few problems on Codeforces that use KMP and Z algorithms. I try to order them roughly in increasing order of difficulty, but you might find like some easier than the rest. So feel free to just take a look at all of them. But otherwise, thank you so much for coming. We will be meeting again, same time next week for session 3 in Advanced Track. Yeah, thanks everybody for coming. I'll end the recording right now.